So our first speaker today is Marco Gualtieri from the University of Toronto, and his title is The Stokes Groupoids with an S. Marco.
Thank you very much, John. And I'm really happy to be here at the Simon Center for another string math conference. It's starting to be a really fun series of conferences. Let me just start the timer there. OK, so the topic that I'm going to talk about today is a little unusual for me. As you see, there's no generalized in the title. However, there is Stokes, and the reason for that is actually started with my reading of Witten's paper on a new way of thinking about the path integral in quantum mechanics. I realized when reading that paper that I didn't understand the Stokes phenomenon, and I started asking around, and I wasn't really satisfied with the responses, and so I decided to study it myself, and I was quite shocked to discover this part, that a small and somewhat trivial observation led to a kind of greater understanding of the topic. So I want to talk about that today. And this is a project which is joint with my two PhD students who are graduating this year, Songhao Lee and Brent Pim. And this is actually a picture of one of the Stokes groupoids, but we'll see that later. So I'm first going to explain the main idea, the overall main idea. It's a very simple idea, elementary idea, and I'll tell you the consequences of this idea, and then I'll go through the idea in detail. So the main idea is the following, that, oops, it somehow, yeah, there we go, the main idea. So let's start with the Riemann-Hilbert correspondence. So what is the Riemann-Hilbert correspondence? It's a relationship between a flat connection and the parallel transport that you get from that flat connection. So a flat connection is on a vector bundle over a curve x, say. I'll stick to curves for this talk. And so this gives you a kind of infinitesimal isomorphism between nearby fibers. And if you integrate that, if you solve the differential equation that the connection gives you, you obtain these parallel transports, which are isomorphisms from one fiber to another fiber. And this parallel transport depends only on the homotopy class of the path gamma that you use to solve your differential equation. And so, so here, from this point of view, I want to think of the left-hand side of the Riemann-Hilbert problem as a representation of the tangent sheaf. So here we see that, for each vector field, I can put the vector field down here into nabla, and I get an operator on the sections of E. And this is a representation of the Lie algebra of vector fields because of the fact that this connection is flat. So the flatness of the connection means that it's a representation of the tangent sheaf. On the right-hand side, however, what we see is that it's a representation of a different kind. For each path, or for each homotopy class of path, you have an isomorphism. And if you have two paths which concatenate, then you get the composition of these isomorphisms. And so this is what is known as a representation of the fundamental groupoid. The fundamental groupoid, unlike the fundamental group, which is just all loops beginning and ending at one fixed base point, consists of all paths up to homotopy fixing the endpoints in X. So this fundamental groupoid, you may be, let's see, where do I get the chalk? So the fundamental groupoid, maybe the simplest case would be the fundamental groupoid of a circle, which is nothing but a cylinder where each point on the cylinder represents a homotopy class of path between 2 points on the circle. So if I'll draw the circle here, if I have a path joining these 2 points, then there are several homotopy classes of paths depending on how many times we cycle around the circle, and each one of these is represented by a point on this cylinder. The reason, and of course, note that because S1 is one-dimensional, the fundamental groupoid is two-dimensional because you can basically, the degrees of freedom are that you can vary the initial point of the path and you can vary the end point of the path independently. So that gives you a two-dimensional space. Okay, so another way of saying this, an important way of thinking about this, is that this P gamma gives you an isomorphism from fibers over initial points to fibers over endpoints. And one way of thinking about it is that if we pull back the bundle E by this map S, then we get an isomorphism to the pullback of E by this map T. Okay? And what this means is that S is somehow the universal initial point. For each path gamma, S picks out the initial point of the path, and T of gamma picks out the target of this path. And so here the source map is kind of this diagonal foliation, and the target map is the other diagonal foliation, kind of intersecting at 90 degrees. So in other words, take your bundle E, which is a bundle over a curve, pull it back to this surface, pi1x, via the two maps S and T, and P is simply an isomorphism from this pullback to that pullback. And of course, this P has to satisfy the condition of being a groupoid representation, so that if gamma concatenates with gamma prime, then the P gamma composes with P gamma prime. Okay, so what I just explained is the standard Riemann-Hilbert correspondence, how to integrate a flat connection. Now, Riemann-Hilbert is much more interesting and important when we twist by a divisor and we allow our connection to be singular along a divisor D. So now our data is a curve X with an effective divisor D. This effective divisor is exactly where the connection is allowed to have poles. And such connections typically look like this. They look like near such a pole. It looks like D plus AZ dz, which is holomorphic. I mean by this notation that this is holomorphic. But there's a prefactor which is z to the minus k if the divisor has degree k at the point 0. So here we have this. This is a typical meromorphic connection. So when you do this when you allow these meromorphic connections, you no longer have this theorem. Instead, what happens?
Is D irreducible?
I'm sorry?
Is D irreducible?
I'm talking about a curve, and D is an effective divisor on a curve. Yes, that's right. Yeah, the higher multiplicity is. Yeah, I'll mention that here. So when you have such a meromorphic connection, what you do get is a representation of the fundamental groupoid of the complement. Okay, so what I said, of course, that's a triviality from the previous slide because it's holomorphic on this complement, and therefore I get whatever I said in the previous slide. On the other hand, near the poles, you do get extra local data, and this local data can have two very different forms. If the pole has order 1, you have Levelt data, which is basically a filtration of the generic fiber by the order of singularity. What happens? If you take a point in the generic fiber and you drag it into the singularity, this will go to infinity at a certain rate, and that rate determines a certain filtration on that fiber, on the original fiber. And so you get these filtration, which are called Levelt data. And if you have higher order poles, then this Levelt data kind of metamorphoses into Stokes matrix data. So we get these Stokes matrices in the higher order pole case. Okay, so now we get to really what the main idea is. And this is going to seem at first glance to be an utter triviality. So the thing which I'm proposing is to view a meromorphic connection not as a representation of the tangent sheaf with singularities, no, but rather as a representation of a different Lie algebroid. This Lie algebroid is the twisted tangent bundle. It's the sheaf of vector fields vanishing at D. This sheaf has a generator, a single generator in every neighborhood of a point, and so this forms a vector bundle. Of course, it's just a line bundle. It's just the tangent bundle twisted by this line bundle. And this sheaf of vector fields vanishing at D has a bracket itself. Of course, if you have two vector fields vanishing at D and take their Lie bracket, that will also vanish at D. And so this A behaves for all intents and purposes like the tangent bundle. Therefore, I want to consider this bundle rather than the tangent sheaf. Okay, and so this is what is known as a Lie algebroid. I'm going to review that concept again in a minute. But this is a Lie algebroid, and like the tangent bundle, it can be integrated to a Lie groupoid. For the case of the tangent bundle, we got the fundamental groupoid, and that was how the Riemann-Hilbert correspondence went. For this algebroid, we get another groupoid, which is not the fundamental groupoid. It's a modification of it. And this is one of the simplest possible Lie groupoids. It's a two-dimensional surface, just like this, with two maps to the base curve x, which are both surjective submersions. So it's a very nice, smooth, two-dimensional complex manifold equipped with two maps to the base. It just is not the fundamental groupoid. It's a different groupoid. And one of the main parts of our paper is to describe these explicitly, something which apparently had not been done before. Once you have this groupoid in hand, you get an equivalence just like before, that representations of the Lie algebroid, which correspond to meromorphic connections, in a way I'll describe again in a minute, you get an equivalence of categories with the representations of this groupoid. Okay, so that is the kind of the main statement. For people who are experts in Lie algebroids and Lie groupoids, what I'm saying here is perhaps not so surprising. This is a version of Lie's third theorem for Lie algebroids and Lie groupoids. But the consequences of this are kind of interesting. What do you get? I'm just now telling you what the results of the whole project as it stands today are. So with this point of view, we obtain the following four things, and probably more, but this is all I can really speak about today. One thing you certainly get is a new explicit family of groupoids. If you're interested in groupoids, you get this nice family of groupoids, which depends functorial on a curve with an effective divisor D. And the importance of these groupoids is that they serve as the universal domains of definition for any system, any ODE with singularities bounded by D. In other words, any system that you have that has singularities bounded by D has its solutions which are well-defined and smooth only exactly on this space, this space here that I mentioned before. So in that sense, it's a universal domain. It is similar to how Riemann surfaces are the universal domains of definition for holomorphic functions of the complex plane with singularities, with branch points. Another thing that you get is a globalization and a categorification of the idea of the isomonodromy flat connection for the relative moduli space of meromorphic connections. So this is a topic where you study meromorphic flat connections on a curve. You have a moduli space of flat connections on the curve, but then you let the curve vary in families. And as that curve varies in families, so does the moduli space vary in families. And the observation from the turn of the 20th century is that this family of moduli spaces has an Ehresmann flat connection, which allows you to get diffeomorphisms, which are not algebraic isomorphisms, between one moduli space and the other. And this point of view gives you a kind of global way of relating one of these curves, one of the moduli spaces to one of the others, without having to integrate this Ehresmann flat connection. It just goes directly from one to the other. Another thing that you get is a kind of totally clear description of the Stokes data as simply, these Stokes matrices that you get in sectors, they arise simply from a check cohomology construction. So in other words, there is a smooth groupoid cocycle defined on this groupoid, and if you choose a check decomposition and force it to be trivialized in each open set, then you get this Stokes data. So that was, I'm not going to get to a description of this, but maybe we can discuss in person. But I'm going to describe this very carefully and this one very carefully. The last thing that you get is perhaps the most surprising one in some sense, is that you get a new approach to this topic of resummation, or maybe some of you may be more familiar with it in the name resurgence. So the idea is that you take a formal power series solutions to some ordinary differential equation, and you somehow do some transformation to it and get an actual solution. And anyway, we'll see how this point of view that I'm promoting gives you this new approach. So these are the main outputs of the project. So let's go into more detail. So. So any questions about these types of results? Yeah. Is it important that X is a curve? Not really. Not really. Actually, the constructions that we provide in the paper are quite general. The constructions of these groupoids, I mean. And it's important, actually, for this point, to get this categorified treatment, you need to consider the total space of the family of curves. And so you end up working with surfaces and higher dimensional families of curves. And so, yeah, so we definitely need to study this groupoid theory on that. And yeah. OK, so let's just review quickly, because I know that many people do know things about Lie algebroid. So a Lie algebroid is basically a representation. It's basically a replacement for the tangent bundle. It has all the properties of the tangent bundle. So it's a vector bundle, A. It has a Lie bracket on its sheaf of sections. And it has a bracket-preserving map to the tangent bundle, which allows you to compare it with the tangent bundle. So you can take any section of A and just map it to T, and you get a vector field. This thing is a Lie morphism, meaning it's bracket-preserving. And it satisfies this Leibniz rule, which is no surprise. The only thing is that U and V are now sections of A, and so they don't act on functions directly. In order for it to act by Lie derivative on the function, you need to first map it into the tangent sheaf, and then act on the function. But it's basically the same Leibniz rule that the Lie bracket of vector field satisfies. So I just repeated it here. A Lie algebroid behaves exactly as the tangent bundle does. It has a de Rham complex, just as the tangent bundle does, and so on and so forth. Examples, I already mentioned one, T twisted by minus D. These are the vector fields which vanish on a divisor D. They have a de Rham complex, which is just D composed with the inclusion of the one forms into the meromorphic one forms. Another example, which is kind of interesting, people may have seen before, is if you fix a number, a complex number, you can take the algebroid to be just the tangent sheaf, but you modify the bracket to be a lambda times the usual bracket. And then you modify the identification of Tx with Tx. This is the identity map, except multiplied by lambda. And so this gives you a slight modification of the de Rham complex, where you just multiply D by lambda. And another really important example is if you have a manifold of higher dimension, and if you have a foliation of it, right, then the tangent spaces to that foliation gives you a bundle which has a Lie bracket on its sheaf of sections, which behaves, as you would expect, as a nice replacement for the tangent sheaf. And in fact, in algebraic geometry, they just call it, for example, the relative tangent sheaf for the foliation. And so you get another example of a Lie algebroid. And there's many other interesting examples of Lie algebroids, especially in complex geometry and generalized complex geometry and Dirac geometry. But I'm not going to talk about those. So since since a Lie algebroid is nothing but a replacement for the tangent bundle, you can also have Lie algebroid connections and Lie algebroid flat connections. So you could consider a vector bundle E equipped with a connection where you just replace T by A. So this is now an algebroid connection, and it satisfies the same type of definition that you would normally have for a usual connection. And here we see that, as an example, if I take the algebroid to be T twisted by minus D, T twisted by minus D has a generator, Z to the K times the fundamental vector field. And its dual, therefore, has a generator dz over Z to the K. And so this means that if you wrote this type of connection in this basis, you would get D plus something holomorphic times this generator of A dual. So you can see here, this is the A dual piece here, and this is a holomorphic matrix. If I take out this basis for A dual, I just get the kind of local description of the connection becomes something holomorphic, a holomorphic differential operator, plus multiplication by a holomorphic matrix times the generator of A dual. So at this point, it just looks like a kind of reordering of symbols, placing the Z to the minus K together with the dz generator. But anyway, so far, that's what this idea produces. And so we see that representations of A are meromorphic flat connections. Another example is that if we take this lambda modified tangent bundle, then the definition of the connection becomes that of a usual connection except with a lambda, and this is what Simpson and Deling call a lambda connection. And there are, so I just wanted to give those two examples. But of course, this is the main one for us today. So representations of A are meromorphic flat connections. Okay, so now, oops, I wish that it wouldn't do that. Okay, so now let's, oh, I think that it's touch sensitive in addition to.
Did you know how to do the correspondence between representations and complex connections in parallel?
Yeah, so I'll get to that in a second, yeah. Okay, I will answer your question. 1 second. Okay, so let's talk about Lie groupoids then. So Lie groupoids are very similar to this type of object. So they are manifolds consisting of arrows. Rather than paths, I'll just call them arrows. So such a point, before it was a path joining 2 points up to Hammatapi. Now I'll just call them arrows. So each arrow, so it forms a manifold. So it's a manifold of arrows, and each arrow has an initial point in X and a final point in X, which we call the source and the target. And so we have 2 maps, S and T, which map from G to X. And these are required to be surjective submersions. You can see why I want them to be subjective submersions in the next line, because I want there to be an associative composition law whereby if 2 arrows, if this arrow goes from X to Y and this arrow goes from Y to Z, I want to be able to compose them. But in order for that to be a smooth map, I need for the fiber product of G with G over S and T to be smooth. And so it's good that S and T are submersions so that that thing is a smooth manifold. And so M is a smooth map. Every point also has an identity arrow. Here, the identity arrows are the points along the circle, which represent kind of constant paths up to Hammatapi. And that's true for any groupoid. So each point in the base space has an identity, and so therefore the base space, which here is the circle, is actually embedded as its space of identity arrows inside the groupoid. And every arrow has to have an inverse. So we see that here are 2 kind of basic examples, the fundamental groupoid, which I already discussed, and here's a really silly example, a very simple example, which is the pair groupoid, which is just the product of X with itself, which has this very simple composition law, kind of the most obvious possible composition law, where you kind of forget about Hammatapi classes in that way. Here's another example of a Lie groupoid, a much larger class of Lie groupoids. These are, however, coming from Lie groups. So this is, given a Lie group K acting on a space X, right? Then I can say that K cross X is a groupoid where the source of a pair Kx is the initial point X, and the target of this arrow Kx, I'm thinking of Kx as an arrow, is what happens when you act on X by K. And so the source and target are given in that way. And there's an obvious composition law whereby you can act by 2 group elements and go from X to Kx, and then from that to K prime times Kx. Okay, so this is a way of viewing a G action or a K action as a groupoid structure. And here, if we just take the simplest case I want to describe is the action of the complex numbers on the complex plane by taking U and exponentiating it, multiplying by Z. This gives a groupoid structure on this C cross C. So it's a 2-dimensional complex manifold. There's a groupoid structure, and I'm going to show you what it looks like. It looks like this. This picture, so a point, so this axis is the Z axis, and this is the U axis. So this point, ZU, has source given by Z. So the source fibers are the vertical fibers. So a point here indicates an arrow that goes from here to wherever this other foliation intersects the identity bisection. So maybe this is a better example. This point here represents an arrow going from here to here. So it goes from this point to this point. And you can see that if you have a point here which goes from here to here, and a point up here which maps it to out here, then you should be able to compose these 2 points to get a point up here which has this point as its source and this point as its target. So there's a composition law on this C cross C, which is uniquely determined by this pair of foliations. And the important thing about these 2 foliations is that they're generically transverse, as you can see, but they fail to be transverse exactly over the fixed point Z equals to 0. So the fixed point is exactly where the 2 foliations line up, and although each of the foliations is perfectly smooth, It's a perfectly well-defined one-dimensional foliation. The singularity is, you can observe the singularity by seeing where the two foliations coincide. But each foliation by itself is perfectly smooth. So this is a picture of the action groupoid. So Alain Connes wrote in his famous book that it is fashionable among mathematicians to despise groupoids and to consider that only groups have an authentic mathematical status, probably because of the pejorative suffix oid. I didn't really know that oid was a pejorative suffix, but I kind of understand what he said. One time I went to speak to Richard Melrose about his work on groupoids. I mean, he's written many, many papers on groupoids, and he excused himself saying, I'm sorry, I have to go and get some cream for my groupoids. So I think Connes is correct. There is a despisement of Lie groupoids. So we're going to see this despisement come up later. But the point here is that what I'm going to show you is that the groupoids that occur in the higher order case for k greater than 1 are not action groupoids of a Lie group. And so they're not related to a Lie group. They're intrinsically groupoid-like. Okay. So given a Lie groupoid, and here I should really draw a picture. This is perhaps the most important slide. So if you have a Lie groupoid, you have the source fibers. So any point here has source this point. So here I'm drawing x as this. This is the x embedded as the identity arrows. And these are the S fibers. Okay, and then you have the T fibers. I'm drawing them as transverse, although they don't necessarily have to be transverse. So here what I'm trying to explain is the analog of the classical result that in order to get the Lie algebra of a Lie group, you need to take the tangent space at the identity element. In other words, you have to take the normal bundle of the identity element. So what you do is you take, for a Lie groupoid, in order to extract the Lie algebroid on X, you take the tangent space. I suppose there's probably colored chalk here. You take the tangent space to the S fibers, or maybe more invariantly speaking, you take the normal bundle. So if you take the normal bundle of the identities, this produces you a vector bundle over X, which is the Lie algebroid. That's how you extract the Lie algebroid of a Lie groupoid. And of course, because the source fibers are transverse to the identity bisection, you can also identify this with the tangent spaces to the S fibers. So this is the same vector bundle. Okay. It's convenient to identify it with the tangent space to the source fibers, because then you can apply the well, for two reasons. So this is the Lie algebroid of the Lie groupoid, which I've drawn here. You take the tangent bundle to the source fibers, and then if you apply the target map, this provides you a map to the tangent space of X. Okay, and this is the map, which is sometimes called the anchor map, which relates this bundle to the tangent bundle. So that's what I've written here, that it's the target projection which provides the relation to the tangent bundle. The other analogy with usual theory of Lie algebroids and Lie groupoids is that normally what you do with a Lie algebra element is that you kind of right translate it over the group, and that gives you a vector field on the group. And then the Lie bracket of such vector fields is the way that you define the Lie bracket on the Lie algebra. So here it's the same thing, that if I have a section of this Lie algebroid, if I take a section, then what I can do is I can take any vector, well, I take the value of the section at a point, and I can right translate it. Okay, and I can do this with every value of the section, right translate it along the T fibers, and I obtain a right invariant vector field on the total space of the groupoid. So every section of A can be extended uniquely to a right invariant section, just like for Lie groups in the same exact way. And so that's how you get the Lie bracket structure on A. So the important thing, and I'll just probably written it there, but let me just reiterate it here, is that sections of A are in one-to-one correspondence with vector fields tangent to a foliation which is given by the kernel of the source map. So in other words, the tangent to the source foliation is, so these are kind of right invariant vector fields. And the important thing about this correspondence is that these are sections of some vector bundle, whereas these are actual vector fields. Okay, so we're going to see why that's so important. Okay, so okay, now a representation. So I'm just kind of going through the basic theory of Lie groupoids. If you have a Lie groupoid, then just as we saw for the fundamental groupoid in the Riemann-Hilbert correspondence, a representation of this Lie groupoid consists of a vector bundle on X and an isomorphism from the sources to the targets, from the source fiber to the target fiber. And it has to satisfy, it has to compose in the proper way. So it's a very, very simple, this is kind of familiar if you know about equivariant vector bundles. Then for the groupoid being the action groupoid, this is exactly the definition of an equivariant vector bundle or an equivariant sheaf. Okay, and so here is kind of the answer to Ludmil's question, which is that how do you, if you have a flat A connection, and if you know that A is the Lie algebroid of a Lie groupoid, then how do you integrate it and get such a representation? And here we need to use this fact. Okay, so the proof is very simple, actually. If you have a flat connection, then you can pull it back by the target fiber. So you pull back your vector bundle to the entire groupoid by T, right? And this thing now it will have an action by these right invariant vector fields, right? So rather than having an action of the sections of some vector bundle, now it has an action by actual vector fields along the direction of the source fibers, right? And so so you end up having a usual flat connection along this foliation F. On the other hand, the source pullback, well, if you pull back a bundle along the map defining a foliation, that will obviously be flat along the foliation. And so this is trivially flat along F. And so what we do is that we take the bundle, which is, so the source pullback of E and the target pullback of E, they actually are identically equal along the copy of X, right? But each of them has flat connections along the source fibers. So we can take that canonical identification and just flow it by this flat connection along the source fibers, and we get an isomorphism between these two bundles on the entire groupoid. It may be extended uniquely to a map like this. And this uniqueness statement depends on the fact that the S fibers, that each one of these fibers must be simply connected. And so that's the only kind of technical requirement, which we do spend quite a bit of time with in the paper. But anyway, this is the basic argument for which by which you get this representation. As you can see, so if you think about it, maybe I've written it here. So this is the Lie third theorem for Lie algebroids and Lie groupoids. There's an equivalence of categories between representations of A and representations of G, the groupoid. And you're using nothing more than the usual existence and uniqueness theorem for non-singular ODEs, because you've reduced the problem to having an action by an actual foliation that you can actually integrate without singularities. Okay, this is the point. I'm sorry? Yeah, so this is an equivalence of categories for the Tanakian structure. Yeah, I'm not sure what to say about that, but maybe it will be clear from what I'm going to say later. Okay, so right. Okay, so So that's the end of the theory. Okay, all the theory is done. I don't need to continue with this theory. What I'm going to do now is kind of explain probably the most important part of our paper, which is that we provide concrete examples of all of these things, and we see how they affect actual solutions to systems like, for example, the Airy system and similar systems. So let's look at the simplest example that's contained in our paper. In our paper, we provide explicit constructions for all of these fundamental groupoids twisted by D. The construction is done using these things called, well, I guess we could call them meromorphic oppers. They're kind of meromorphic projective structures on the curve, which come from the uniformization of the complement of D. But I'm not going to get into that today. It's not important for what I want to say. We also produce explicit examples of the pair groupoid twisted by D. Remember that in the same way that we had the fundamental groupoid, we also had this kind of baby example of X cross X, which was the pair groupoid. There's a simpler example for any curve with effective divisor, and we describe this as well. But let me just give the simplest family of examples, which we call the Stokes groupoids, Sto K. You take the complex plane, and you take a pole of order K. The groupoid will be C cross C, just as we had for the action groupoid of C on C, except that the structure maps are as follows. So the source of an arrow ZU is Z. The target of the arrow ZU is this exponential factor times Z. Okay? And the composition of two of these arrows is given like this. As you can see, this thing is non-algebraic. This is holomorphic, but non-algebraic. The pair groupoid, we like it because it is algebraic. It's an algebraic construction. But anyway, what I have to say is not really so important. It's not so important for today which one we use. So here is an example of the Stokes groupoid for a kth order pole. And so what I'm saying is that if you have a system with a kth order pole, say you take the Airy equation, which is a third order pole at a single point, then the solution to Airy is well-defined, unique, and smooth on this space, and this space is characterized by that property. This is the universal domain of definition for any system with a kth order pole at 0. Okay? And as you can see also, for k equals to 1, this factor here, the z inside here, goes away, and it becomes e to the u times z. And so for k equals 1, it coincides with the action groupoid of C on C. But for k greater than 1, this is not an action groupoid of any Lie group. So for the higher order case, the key thing is that it's not related to a Lie group. It's really a purely groupoid. So here is the picture you saw before. It's the Sto1 groupoid, or in other words, the action groupoid. And what happens if you increase this 1 to 2 is that it changes in this way. Okay, so I've drawn it in such a way that the source fibers remain the same, but the target fibers are now being modified. It's still the case that every point the target fiber intersects the identity bisection at a unique point. So this foliation still has the property that each leaf intersects the identity bisection in a single point. But for example, this is no longer true that a constant value of u intersects in exactly one point on each target fiber. For example, here you can see that if I cut this with a line, it'll hit this kind of exponential curve in only one point. This is no longer true here. You kind of get two points, and that's related to the Sto2, and also related to the Stokes matrices. Okay, so let me just quickly describe some of the main applications. So I think I have about 7 minutes or so, maybe 6 or 5 minutes. So here is one of the consequences of the existence of this groupoid. Okay, so if you have a fundamental solution of a system, what is a fundamental solution? It's a flat basis of solutions. So of course you cannot expect to have a flat basis of solutions for a system, which is globally defined, because then the system would be trivial. right? So that's why your fundamental solutions typically are multi-valued, they're typically singular, and they also can have zeros, which is a very strange thing for a parallel transport to have. Parallel transports should be isomorphisms always, okay? But nevertheless, you typically write fundamental solutions as multi-valued and singular. The Airy function would be a perfect example. The Airy function is a component of the matrix, the fundamental solution matrix, and that thing has zeros and has singularities, etc. So if you take a fundamental solution which is multi-valued and singular, etc., and you form this combination which says that if you want to kind of do a parallel transport from one point to another, what you should do is evaluate your fundamental solution at the initial point, invert it, and then multiply it by the value of the fundamental solution at the target point. And that will give you the means to transport a vector in one fiber to a vector in the target fiber. So on the right-hand side, we have a combination of singular and badly behaved fundamental solutions. On the left-hand side, we have a groupoid representation, which a priori we know has to be smooth on the groupoid. And so we see that all of the bad behavior of psi is cured by pulling it back in this particular way. This is called actually the groupoid differential for the Bott-Schulman groupoid complex, but never mind. This particular combination will produce a smooth solution on the groupoid. And so this is what I mean by saying that this thing is the universal domain of definition for solutions. This is basically the universal parallel transport between any 2 points, including kind of limiting parallel transports as you go into the pole. Anyway, so this is the expression to keep in mind. And so that's the first kind of maybe easiest application, is that we get these domains, which are the correct domains to study solutions to these systems. But a slightly less obvious application is the following. Suppose, now we're really going back to ODE class. I don't know how much you remember about irregular singularities in your original classes in ODEs, but let's review. If you try to solve this simple, this is a inhomogeneous ODE, but never mind. If you try to solve it with power series, you get this result. Notice the n factorial. Therefore, this thing is definitely divergent. It's just not a convergence. The radius of convergence equals 0. Okay? So these are called formal solutions, and there is a very extensive and complex, complicated, let's say, theory developed by Shibuya starting in the 50s, Morel, Ekal, Ramis, etc., a huge literature devoted to taking such a formal solution and resumming it in order to obtain an actual solution. Okay. So what I'm claiming is that there's an application of this groupoid theory to kind of explaining what is going on here, what is really going on here. Instead of thinking of this just as a solution to an inhomogeneous problem, I'm going to recast it to an equivalent form. I'm going to say that this function f is really intended to be an isomorphism between this connection and this connection on the complex plane. So this connection here is a diagonal connection. It's a sum of 2 connections on line bundles. This one has an off-diagonal term, and this would have Stokes matrices. So this thing is not equivalent to this. They're genuinely different isomorphism classes of connections. Nevertheless, you could try to find an isomorphism from this to this. You could try to do this. And if you tried to do that, that would be essentially trying to find a function satisfying this equation. If you just write this intertwining relation, if you just write it out, you'll get this equation. So this equation is equivalent to finding an isomorphism from here to here. Both of these connections, however, have second-order poles at 0. This one was, of course, chosen because it approximates this one. Okay, but never mind. So both of these connections are representations of this algebroid. And so, therefore, the representations of the groupoid, they would be defined on STO2, on the STO2 groupoid that I showed you a picture of. That was the kind of more complicated picture. So what I would like to do is to kind of work out what these groupoid representations actually are on this STO2 groupoid. For this, I'm going to use a different coordinate system just for convenience. It's really not an essential point, but I'm going to use coordinates z and mu for which the source is z and the target is this combination. So it's just a rational function in z and mu. But this is just a coordinate change from the ZU coordinates that I used before. OK, so first of all, what is the groupoid representation corresponding to nabla 1? Well, corresponding to nabla 1, all I need to do is find a fundamental solution and form this groupoid differential. Now, a fundamental solution to that system is just e to the minus z inverse. You know, if you look at this, this is basically looking at f prime equals z to the minus 2f. That has a solution, oops. That has a solution e to the minus z inverse. So I take this pullback and this pullback. Notice that both of these have essential singularities at z equals to 0. If I pull them back to the groupoid using the coordinates I mentioned, you get this, which is, of course, smooth, unique, single-valued, and doesn't vanish. So this is really a parallel transport isomorphism defined for all points on the groupoid. So we see the first incarnation of the first principle, that it is a domain of definition for the solutions. Now, on the other hand, now that we have a solution for nabla 1, and since we have and if we had an isomorphism from nabla 1 to nabla 2, then we could just use the isomorphism in here to get the groupoid representation for nabla 2, right? I mean, if we have an isomorphism from nabla 1 to nabla 2, then we could obtain the solution to nabla 2 from the solution of nabla 1, and then I get this expression, which is phi psi 1 phi inverse. Now, we don't have an isomorphism between these two connections because they really are different. They really are non-isomorphic. However, we do have a formal isomorphism. We do have a formal isomorphism because we solved that equation in formal power series. So this means that from a formal point of view, the second groupoid representation is this combination. You take the first actual solution, put it in here, and then conjugate by this strange combination of target pullback and source pullback of this formal power series. And we get this matrix just by doing this matrix multiplication. And we see here we have something smooth, and then something formal, which is a combination of source and target pullback of the formal solution. And here is the key point. The key point is that while it is true that this is formally the case, that these are formally related in this way, we also know that psi 2 must be smooth and well-defined on the groupoid STO 2. We know a priori that this thing psi 2 is actually smooth and convergent. So this thing, although it's created from the formal solution, must be convergent. And indeed, if we take this divergent series and we compute this combination just by some combinatorial rearrangements, I mean, this is a term by term, it's a finite number of operations, we get this infinite series, which indeed is convergent. So it's an incredibly simple algebraic manipulation of the divergent series by which we produce a convergent series. And this is completely different. It's completely different from the usual Borel method of resummation. If anyone is familiar with that thing, you need to take the coefficients, divide them by n factorial, then you need to do a Laplace transform. It's a nightmare. So this, for some reason, this is the way that you kind of obtain it directly. So this is what I mean by having a summation theory for divergent series. And so in the final slide, I'll just kind of remind you of what Abel was thinking right before he died, under age 30. Divergent series are in general something terrible, and it is a shame to base any proof on them. We can prove anything by using them, and they have caused so much misery and created so many paradoxes. You can almost sense the despisement that he has for divergent series. And so somehow I think that the moral of my talk is that despising the groupoids and despising the divergent series was a good strategy for having them cancel each other out. Thank you for your attention.
We have time for a few questions. Yes?
Is it possible to write the Stokes groupoid in terms of paths, which you write fundamental groupoid?
Yes. So there's a famous result of Krajanic and Fernandez, by which any Lie algebroid. Well, so what they proved was so unlike the usual theory of Lie algebras and Lie groups in finite dimension, whereby every Lie algebra has an integration to a Lie group, For Lie algebroids, this is not the case. There are obstructions to integrating to Lie groupoids. And Krajnic and Fernandez described all of the obstructions, and the way that they did this was by using a path construction by which they constructed the groupoid integrating any Lie algebroid. And they checked when is this thing smooth, and they found the obstructions in that way. So from their point of view, there's certain obstructions to check here. You check them, they're all 0. And so there is a groupoid, and they leave it at that. The question of the explicit construction, and anyway, if you look at the paper, you'll see the nature of the explicit construction is very useful, because then you can understand, for example, symmetries of the groupoid. And there's a lot of things you can understand about the groupoid once you have an actual realization of it. But indeed, the existence of the groupoid follows from these results of Krajnic and Fernandez about the obstruction theory. And it's exactly by that construction, yeah.
Does this give you a new way of understanding a chaos word?
Understanding what?
A chaos word?
Yeah, so we're working on that to see exactly how this weird transform, if I write it in an integral form, that I should recover exactly a Cal's kind of procedure. But we've only seen hints of that. We haven't got it all down, pinned it down yet. But it should definitely explain the procedure of a Cal, why it is that way. It has to do with integrating along source fibers of the groupoid. And so you get this integral formula for the representation. To be continued, yeah.
I have 2 questions.
Oh, okay.
At one point you mentioned you need simple connectivity of the source fibers.
Yes.
That's a result you prove in general, that's an assumption you make?
So just as in the Lie algebra and Lie group case, for each Lie algebroid, you can have a tower of Lie groupoids, which are kind of distinguished by the fundamental groups of the source fibers. So there's a kind of discrete family. And what we did in our paper was to construct the lowest one, which is kind of what we call the adjoint groupoid, which is kind of similar to like PGLN, the smallest group. And we also construct the source simply connected one by a different construction. Although we didn't explore it, the ones in between are kind of given by Bélier curves. They kind of, these dessins d'enfants, they kind of distinguish all the different ones. But anyway, the point is that by using the uniformization of the complement of the divisor, we're able to construct this source simply connected groupoid. Yeah, yeah.
And lastly, did you get the same answer that one gets by Borel summation?
Yes, definitely. Yeah, yeah. You get the same answer. Yeah. In fact, that
you have to get the same answer.
You certainly do. Yeah. You
have to reproduce ambiguity.
No. I mean, Borel's resummation is not supposed to be. I mean, even though the description is given in a kind of. I mean, it depends. It seems to depend on choices of coordinate, but in the end, it's not. It doesn't. Yeah.
No, it's ambiguous because typically you have poles on the integration.
Yes, yeah, but that's an ambiguity downstairs. When you pull that back by source and target, then it's unique. That ambiguity has to do with the Stokes matrices when you pass one of the rays. Yeah, yeah. No, that's right. Yeah.
Any other questions? If not, thank Mark.
Thank you.